All right, now that we've talked about how the scattering intensity is different, or how the scattered intensity is affected by single electrons and by single atoms, well, we want to now look at what happens when we take those electrons and atoms and put them in a periodic structure like we've talked about in the previous section. And so that's what we do with the structure factor. So this is what happens to the intensity when the diffraction intensity of a peak when it's part of a structure. So when the atom and electrons are part of a structure. So the structure factor refers to interference between scattering atoms. Right? So we basically take all that knowledge from atomic scattering factors and try to put those together when they interfere and interact into a unit cell. So when we talk about diffraction, this is why we have to know a little bit more about crystal structure and crystallography, because when we get to structure factor, the way that the intensity is going to be represented is strongly dependent on the structure itself. And so we need a way to describe it because we need to be able to calculate these structure factors. All right, so let's look at an example. So if we have, if there is more than one atom per unit cell, atom in the unit cell, such as 4 atoms that we have in FCC, or face-centered cubic structure, then the intensity from certain crystallographic planes become extinct due to interference between atoms. So basically, the presence of additional atoms in the face-centered cubic compared to, say, simple, where we have only one atom in the unit cell, that existence of 3 more atoms makes it such that in certain directions or on certain planes, the diffracted intensity goes away because we have destructive interference from those additional atoms. So let me kind of give you an example of this. And to do this, we're going to compare a couple different structures. So let's compare 2 unit cells of the same size, but one is what we call base-centered, and the other is body-centered. So I'm going to switch pages here, and then we'll redraw these, and I'll give an example of this interference. All right, let's compare those 2 types of structures, base-centered and body-centered. And I just drew 2 unit cells to start here, and we know that they all have the simple arrangement, so atoms on the vertices or corners. So both of them have that similarity. They both have the same size, so same volume, so they're both the same structure. So even if you can see differences here, it's just because I sketched them a little differently. But this one's base centered, and so the base in this case is going to be the bottom and the top. So I'm going to have an atom here in the center of the base, and then one in the center of the top. And I'm just going to draw that line so you can kind of tell how far apart they are. With body centered, it's in the body of the volume, so it's right in the center of the volume is where my extra atom is, and then I would have another one above this unit cell. So the distance between these 2 points is the same as the distance between these 2 points over here. It's just that this is shifted up in the z direction by 1/2. So that's the only difference. So otherwise, these structures are the same. And so we want to look and see what the differences are here in terms of diffraction. So let's look at the 001 plane for diffraction. So in terms of Bragg's conditions. So I'll draw the angle, the planes here. So effectively, I'm drawing the bottom plane. So I'll call this 1 and this 2. So this is 1 and 2. So those just the bottom plane and the top plane. So I'm just redrawing it down here. So in this case, I have, if I'm just basically looking at it from the side on and drawing it in 2 dimensions, right? I'm going to have the atom here, then the atom here, and the atom here. So that's why you see the 3. And they look like they're in a row, but obviously it's 3 dimensions here. And then on the body-centered side, if we look at the same thing, we have, plane 1 and 2, but we also have atom in the middle, right? So when we draw that, we have to draw the atoms on the top, atoms on the bottom. So these are 1 and 2. But then we have this one right in the middle. So I can call that 3 if I want. Doesn't really matter what I call it. But basically I have a mid-plane. It's halfway in between where this atom is located. So this is 3. So I already have some differences there. So now if I look at the condition for diffraction, according to Bragg's law, I have to have the angles theta. So this is beam 1 and 1 prime. So the incident beam and the diffracted beam. And then the same thing for the second beam. Has the same geometry. So this is beam 2 and 2 prime, right? And this is also, this distance here is c, the distance, the vertical distance here. Okay, so that's what we have in the case of the base-centered. We have diffraction in this case. However, let's look at the same scenario in the case of the body-centered. So if I look at the same angle, so theta and theta, and then again, in this case, so this is beam 1 and 1 prime again, this is beam 2 and 2 prime, but we have this mid-plane, right? This mid-plane can cause diffraction as well, and so I would have 3 and 3 prime. So basically that extra, the fact that I have the middle atom halfway between these is important, because if we think about the issues here, right? If this causes constructive interference, the extra distance that the second beam travels is an integer value of lambda, right? That was 2d sine theta, right? So that satisfied the Bragg condition. So that also would mean that the same is true for beam 1 and 2 over here. But we now have a third beam halfway in the middle. And so it's basically completely canceling out what we see in those two cases, right? So for every 1 and 2, we're going to have a atom in the midplane there that's going to perfectly cancel out, or what we call annihilate. So basically 3 annihilates 1 and 2. So its presence there cancels out what we had for what we had for 1' and 2'. So the fact that it's right there in the middle cancels that out. So in this base-centered, we do detect the 001 plane in diffraction. But for the body-centered, we don't detect the 001 plane because it's getting canceled out by the midplane here. So we don't see that in diffraction. So this means that regardless of what we do, we shouldn't expect to see the 001. It's not to say that the 001 plane doesn't exist. You know, we know it's there, right? We can always draw a 001 plane. But the way the diffraction works is it's being canceled out by the extra atom in the middle, whereas this one had the extra atoms in the plane, the 001 plane. However, what we do see is that we can observe the 002 at another angle. So for body-centered structures, we end up seeing the 002. It's just going to be at a different angle where the interference here doesn't take effect. So obviously, if you're thinking about the way that a structure is going to interact with various atoms, it doesn't make sense to kind of draw these and go through these sort of beam diagrams for every different scenario and every different plane. So we need a more formalized way to come up with how to obtain these structure factors, how we're going to identify which planes are observed intensity-wise, which ones are not, and then the varying degrees of the intensity between them. And so we want to formalize this instead of just kind of relying on these examples. And so that's where we can calculate the structure factor, and I'll show you that here in a second. Okay, so now we can look at the structure factor calculation, which tells us about how the arrangement of atoms in a unit cell affects and interferes with X-rays, and that gives us the ability to calculate. So the structure factor we refer to as capital F. So you saw the script F for atomic scattering factor. This is capital F, and then HKL to denote which plane we're talking about. So this gives us the sort of combined scattering effect of a structure for a given set of planes HKL. So the equation is a summation from little n to capital N, and then we have, sorry, this should be lowercase, the atomic packing factor, sorry, the atomic scattering factor of the n atom times an exponential term of 2 pi I, the imaginary number, and then inside of this term we have HUN, H times U sub n, plus K times V sub n, plus L times W sub n. So just to kind of go over what's in this equation, n represents the number of atoms in the unit cell. Right, so how many atoms do we have? So if we're talking primitive, we only have one atom per unit cell. So this is a really simple summation. We just have to deal with one atom. If it's FCC, there's 4, and so forth and so forth, right? So that's just the number of atoms that we have. And then N is a specific atom. So basically, any given one that you're looking at through the summation of the total. So that's basically kind of a counting mechanism. And then those specific atoms are at position UN, VN, and WN. So those are the point coordinates of the specific atom with N as its indicator. And then the script F sub N is the atomic scattering factor for atom N. All right, so a couple other notes that I wanted to bring up while we're talking about this is that we have this sort of exponential of a 2 pi I term. And so this is kind of important. There's an imaginary number in here, and this has some implications for the math that we have. And so one realization that we can make is that if we have an exponential I times something, so some term, I'll just put theta here, then we can also look at that in terms of exponential. When you see it like this, some people aren't familiar with this writing, but that's just e to the power of whatever. So that's the same form. So if you're just not familiar with that, but we can also write it this I term as cosine of the term theta plus I sine theta. So it kind of makes it longer and so forth, but there's some reasons to using this format. So that would make it, so if I plug that definition of this term in, this would give me the following expression. So it definitely makes the form of the equation longer, but it can be useful for some of the other, some of the actual calculations. Okay, so I do want to make a couple additional notes about sort of the math here, what I'll call math notes. So when we have an exponential times pi I, and it's odd, so basically this form of the expression becomes about even or odd. So when it is odd, this term is equal to -1. So it really simplifies this expression. And if we have an even number times pi I, then this is a +1. And so we can kind of formalize that by saying that the exponential times n to the pi I is equal to -1 raised to the power of n. So that's kind of how we can write this. But you'll see this comes out, and so when we plug in our planes and our location of the atoms, we'll be looking to see what effect it has on even, odd, and that will determine the values we get for the structure factor.